Hey guys, my name is Alan Yu and this is Physics Lab 5, our final lab. I chose to model a tennis serve. The objective of this lab is to observe the motion of a tennis serve and model the interactions involved in the initial toss of the ball in order to determine the work done on the ball to achieve the perfect height. To do this, we will first view the tracker analysis and then proceed to creating the computational model using two fundamental principles, the momentum principle and the energy principle. In the end, we see that the work done on the ball is calculated to be about 0.56 joules, with most of the initial energy from the work done being conserved, with it being slightly dissipated by an unaccounted drag force in the model. My clip is assumed to begin just after the ball leaves my hand. It starts from frame 10 and ends at frame 24, with each frame measuring about 1/30th of a second. The video was calibrated using the diameter of a tennis ball measuring about 6.7 centimeters. The axis was placed so that the origin is on the ball during the first frame, with the positive y-axis pointing up and the positive x-axis pointing to the right. After tracking all of the points, we note the change in the x-axis, but for the sake of this experiment, we will only focus on the y-axis since height is our main topic. We see the general change of position of y position versus time, where the change in y slows down to 0, indicating the ball has reached its highest point. Using the first two y values and the first time step between them, I calculate the initial y velocity using this formula. Now let's move on to building our code using the fundamental principles of physics. The first fundamental principle is Newton's second law, or the momentum principle. This principle is used to update the velocity and position of the ball in our code. From the basic form F equals ma, we see these derivations of updating momentum, velocity, and position for a given time step and net force. In our code, we see that the net force all comes from the weight force. And within our while loop, the velocity and position update formulas are used to constantly update the ball for every given time step delta t. The next fundamental principle is the energy principle. It states that in a closed system, total energy changes can only be caused by work done by an outside force. For our system consisting of the tennis ball, I start analyzing the ball just after it leaves my hand. Work was done by my hand, but I choose to close off my system after that initial input. That's why for the purposes of the model, the work done on the system or the ball is 0. Energy within the system can change forms though. The total energy in the system is all deemed to begin as kinetic energy. As the ball rises and slows down, that kinetic energy is changed into potential energy, and the formula for each type of energy is shown here. In a perfectly conserved system, the amount of potential energy at the top is equal to the initial amount of kinetic energy. In our code, we model and update the change in kinetic and change in potential energies using these following lines. The same formula seen above can be seen in the code shown here to calculate the initial energy values. In the initial position, the initial velocity is at its fastest, so it has the most kinetic energy. And the initial y position is 0, so the potential energy would be 0. I assign one work variable to the value of kinetic energy to compare with the final amount of energy. Within my while loop, I define the initial kinetic and potential energies, calculate the new values for the energies after the velocity and positions are updated, and then calculate my change in energy for that time step. I continuously plot these changes on a graph along with the total energy to examine how the energy is conserved in the system. In this final line after the while loop, I set the final potential energy to a second work variable and print both values to compare the amount of energy in the system at the beginning and end. Now let's look at our completed model. Just by scanning through the model, we see the initial conditions from our tracked video. I inputted the ball's mass of 57 grams and the initial velocity that we calculated earlier. I set my time step to 0.001 seconds and set the gravitational constant. We see our while loop set to stop at the end of the length of the tracker video in every piece of code that was analyzed in detail previously. Now let's run our code and see what happens. We see the ball moving up and stopping just like in our observation. The graph displays the change in kinetic energy in blue, and it is in the negative because it is decreasing, but gradually decreases at a slower rate. The potential energy is in red and is increasing, but gradually increasing at a slower rate. And this green line is the total energy change of the system, which is shown to constantly remain at 0 because no energy is inputted or taken out of our system. Now let's look at the specific values that we were looking for. The initial work value based on the initial kinetic energy is about 0.0558 joules. The final work value based on the final potential energy is about 0.556 joules. This shows that only 0.002 joules of energy were dissipated, so most of the energy is indeed conserved. And the amount of work done on the ball to achieve the perfect tennis serve height, for myself at least, can be rounded to about 0.56 joules, as we mentioned in the results in the very beginning. In conclusion, all we found was the work done on the ball and analyzed its motion in the closed system. The model could have been improved to account for the drag force, but in the end, the energy dissipation was minute, and we were looking for the initial energy anyway. We could attempt to find the force that acted on the ball by the hand, but there's no way to determine an accurate displacement through which the force acted simply through the observed video. But in the end, I know how much work I do on a tennis ball during a perfect serve. Thank you.